Dear student, warm welcome to NPTEL Phase 2 program video course on Geosynthetics Engineering in theory and practice. My name is Professor J. N. Mandal, Department of Civil Engineering, Indian Institute of Technology, Bombay, Mumbai, India. This module 12 and lecture number 54, design of geosynthetics for landfill. I will now show you the recap of the previous lecture which we have covered, that is introduction, landfill classification, some engineered solution for landfill, low permeability clay liner in a landfill system, geosynthetics in landfill system, wet landfilling, bioreactor landfill, leachate detection, collection and removal system. Now I will address slope stability of site liner. You know, the design of the stability of the soil mass beneath the liner system of any solid waste landfill has been carried out. You can see here the slope, and this is the geosynthetic clay liner, or you can give the geomembrane, which consists of a lower geotextile and this bentonite, and then upper geotextile, and then you are providing with the covered soil. Alternative to this geosynthetic clay liner, we can also provide with the geomembrane material. These various landfill lining system to obtain a stable slope. So we want to achieve a stable slope. So this is the slope stability of landfill lining system with unreinforced covered soil. And you also require number of the layer of the reinforcement, that what you call the multi-line side slope covered soil slope stability. This situation of the liner, also sometimes that there is a provision of the providing the leachate collection along this slope, where you may require any geocomposite material or the geonet material. So here also shown the reinforced covered soil. Apart from the geomembrane or geosynthetic clay liner, you can provide with the reinforcement to make a proper slope. You can make any steeper slope or the angle as you like it. So you can provide sometimes the geosynthetic clay liner, also the geomembrane, also the geonet. This all combination of the geosynthetic material. So what will happen, that if we provide the multi-layer of the geosynthetic reinforcement, and there is a possibility to induce the shear stresses through this system. So this is the challenging each of the interface layer, and that are in this cross section. Now if all the interface shear strength are greater than the slope angle, this slope angle stability is achieved and deformation involved will be the small. On the other hand, if the interface shear stress are lower than the slope angle, then it is required that wide width tensile stresses are induced with the overlying geosynthetic material. Then there may cause of the failure of the geosynthetics or for the pull out failure also along the anchor trench or the tensile reinforcement. So, here a different layer of the geosynthetic clay liner or geomembrane or GCL, which is made of the needle punches of GCL, also has been provided. Now, sometimes also you require for slope stability of the landfill liner system, you require some anchor. So, there are different types of the anchor. It may be you can straight forward, you can put some anchoring, digging and can put the anchor trench where you can place this geogrid or geosynthetic clay liner like this, or you can make a rectangular shape, or you can make a V-shaped anchor to make the soil much more stable. So, if sometimes it is also required that anchoring system to make the slope more stable. So, this is one slide shows that lining of the geomembrane on the slope. This is the geomembrane, that black color, and how you have to line it is in the form of the roll, and then you can spread along the slope. We are more interested here the design of the landfill liner. How can we design? The most of the cases we provide with something that thickness of the geomembrane or geosynthetic clay liner, and they are introduced into the landfill in many projects. But one has to be very careful. There are many issues which are need to be addressed for the design of the landfill liner. In India, there is no proper computer program available for landfill design and its stability analysis. Across the world, hydrologic evaluation of the landfill performance, which you call HELP, HELP, that is Schroeder et al. 1994 model, is available for this purpose, which is developed by United States Environmental Protection Agency or US EPA. However, HELP model has several limitations, such as it requires several trials to get the desired solution. HELP model does not give any response during execution, such as suggestion for minimum required tensile value of reinforcement to stabilize the covered soil, response against the choice of wrong values. HELP model cannot perform the estimation of tensile stress in geosynthetics, which is necessary to design the anchor trench, stability analysis in seepage condition, and waste mass failure analysis. Sometimes also in the landfill it has been observed that waste mass itself is failure. So, this is required how to design that. So, based on that we have developed a program which will show you how you can design all those issues. So, different theory and design model along with the design equation proposed by the various researchers, Kohler and Sung 2005, Giroud 1989, Giroud 2000, Join and Mandal 2005, Kohler and Hu 1991, Kohler and Sung 1996, Kohler and Sung 1998, Kohler 1997, Cohen et al. 2002, Cohen 2003, Rickerson 1987 and Rickerson 2000, Rickerson 2002, and Thiel 1998 and US EPA 1993 have been used to prepare a new software named as Landfill Slope Stability Model, which you call the LSS model, IIT Bombay. So this LSSM software was developed using Visual Basic Net in C# language, also termed as Advanced C language. It may widely be used by consultants working in the solid waste field in India and around the world, SONY 2008. The inclusion of graphical interface in LSS model with detailed diagram makes this software much more effective, attractive and user friendly as compared to normal C or C++ or Fortran problem. The landfill slope stability model LSM can deal with the following problem. So I am just showing some of the problem here. I can show you more problem in our program, that is landfill slope stability model. One, stability of cover soil for infinite slope. 2, beneath slope stability analysis without reinforcement. 3, beneath slope stability analysis with reinforcement. 4, beneath slope stability analysis for unreinforced separate covered soil. 5, beneath slope stability analysis for reinforced separate covered soil. 6, seismic analysis for beneath slope stability. 7, seismic analysis for beneath slope stability with reinforcement. 8, seepage force analysis for beneath slope stability, that is seepage is built up horizontally or seepage is built up parallel to the slope. 9, designing of runout length and anchorage trench. Only runout length with the rectangular anchor trench or runout length with the V-shape anchor trenches. 10, application of geosynthetic clay liner or geomembrane liquid containment liner, that is geometric consideration and thickness consideration. So I will show you that some of the that stability of cover soil for infinite slope. Here you can see that what are the forces involved in limit equilibrium analysis of infinite slope. This after Koiner and Sung 1998. Here this W, the weight of the cover soil, and beta is the slope angle, and this is the delta is the friction angle between the geosynthetic clay liner and the cover soil. So this cover soil has a thickness, and also this is the geosynthetic clay liner or geomembrane. This is like a anchor trench, and this W has a component, horizontal component will be W sin beta and vertical component is W cos beta, and N is the normal which is acting along this slope on GCL. And so this force, resisting force will be N into tan of delta, N into tan of delta, what delta is equal to friction angle between the geosynthetic clay liner and the cover soil. So we can calculate the what will be the factor of safety. Factor of safety will be the resisting forces divided by driving forces. That means the resisting forces is N tan delta. So this is the resisting force acting along this slope. So this is N tan delta. So that's why this is N tan delta divided by driving force. Driving force is this, that is W of sin beta. This is the driving force, this acting is downwards along the slope. So, we can write that factor of safety is equal to n tan delta divided by W sin beta. Now, again what is n? So, n is this W of cos beta, this n is W of cos beta. So, you can write n is equal to W cos beta. So, W cos beta into tan delta divided by W sin beta. So, ultimately you will obtain factor of safety Fs will be equal to tan delta divided by tan of beta. From the above equation, it is clear that geosynthetic clay liner or the geomembrane having high interface shear strength will exhibit high stability, that is high factor of safety value. Now, I will give one example, design example of stability of cover soil for infinite slope. Now, property of the side slope and the material used in the LSS model, that is landfill slope stability model, and the HELP model are mentioned below. Factor of safety is find out against the sliding of covered soil, and covered soil slope angle beta is equal to 18.4 degree. Interface friction angle between the geosynthetic clay liner or geomembrane and covered soil, that is delta, is equal to 23.4 degree. So, this is the input data of the format in the landfill slope stability model, and this is slope stability analysis for infinite length slope. Now, this problem statement to determine the factor of safety for a geosynthetic clay liner or geomembrane line slope within the slope is considered in infinite length. Now, here to put the properties, what will be the input data? So, input data will be the what will be the slope characteristics, that means what will be the slope angle in degree. Here slope angle beta in degree will be equal to 18.4. So, then what will be the geosynthetic clay liner or the geomembrane property? That means what should be the interface frictional angle between the geosynthetic clay liner or geomembrane and the covered soil, and that is delta is equal to 23.4 degree. Now, you have to input this data into this model and then you calculate, and then you can have the what will be the output. You can see that factor of safety is equal to Fs 1.301. So, you can make a comment that since the factor of safety value is greater than 1.00, that is the force tending to slide the covered soil, then over the geomembrane or geosynthetic clay liner are less than the resisting forces. So, the design is stable and safe. So, we see that in this model you can just put the properties of the soil and the properties of the geosynthetic clay liner or geomembrane material, and then you can determine that what will be the factor of safety. So, that way you can find out the slope stability analysis. Here result for LSS model was found to be similar as compared to the HELP model. So, case with the infinite length slope stability analysis, HELP model no such option is available, whereas that landfill slope stability model which give factor of safety is equal to 1.301. So, it is a safe. Next to the Venice slope stability for uniform thickness unreinforced covered soil. So, there is no reinforcement and this is the slope, and this is limit equilibrium forces involved in a finite length slope analysis for a uniformly thick covered soil this after Koiner and Sung 1998. This is the thickness, H is equal to thickness of the cover soil, and this is the length of the slope of cover soil, that is L, and this the active zone. So, this is the cover soil whose thickness is H, and W is the active weight which is active in the active zone. Whereas here, well, when the cover soil is slide down in this direction, so there will be a passive wedge. So, WP is also the passive wedge which is acting in this passive zone, and there is the shearing resistance between this soil and which is the value of the pi, shearing resistance of the soil is pi. So, there will be a NP which is acting vertically toward the passive wedge. So, this shearing resistance will acting in this direction, and that is what you call the NC tan of pi, and there is a C, the cohesion value also. So, this is the C value, cohesion in the passive wedge side, and there is also a normal force, that is the Na, which is acting along the slope, and there is a shearing resistance between the covered soil and this subject soil, and that you can say that delta. So, this is delta is acting along this direction, that is N of A into tan delta, and there is also adhesion, and that adhesion is the C of A, and this is the geomembrane material. So, there will be the internal friction between the cover soil and the geomembrane, and that is designated at delta, and C is the adhesion. And apart from that, there is a E of A, that is interwedge force acting on the active wedge from passive wedge. And similarly, this is the E of P, which is interwedge forces which is acting on passive wedge from the active wedge, and that is in kilonewton. So, these are the limit equilibrium forces are acting in finite length slope of uniformly thick covered soil. So, from this you can calculate what will be the factor of safety with this equation, minus B plus minus B square minus 4AC whole to the power 0.5 divided by 2A, where A is equal to WA minus NA cos beta into cos beta, and B is equal to minus WA minus NA cos beta into sin beta into tan phi plus NA tan delta plus CA into sin beta into cos beta plus C plus WP tan pi into sin beta, and C is equal to NA tan delta plus CA into sin square beta into tan pi, where WA I told the total weight of the active wedge, here total weight of the active wedge, and WP total weight of the passive wedge, this is WP total weight of the passive wedge, and NA the effective force normal to the failure plane of the active wedge. This is the active wedge, NA normal force, and also the NP is the effective force normal to the failure plane of the passive wedge, here NP. So, we will be knowing that all this value, that is A, B and C, and then you can calculate that what will be the factor of safety. Here I am giving one design example for Vinit slope stability for uniform thickness unreinforced covered soil. Now, in the problem it is given covered soil slope beta is equal to 18.4 degree and length of the slope L is 35 meter, thickness of the covered soil, that is H is equal to 0.3 meter, unit weight of cover soil gamma is 17.5 kilonewton per meter cube, and cohesion of the cover soil C is equal to 0, adhesion between the cover soil and the geosynthetic clay liner, that is Ca, is equal to the 0, internal friction angle of cover soil pi is equal to 30 degree. So, interface friction angle between the geosynthetic clay liner and cover soil delta is equal to 15 degree. Now, determine the factor of safety against cover soil sliding using the landfill slope stability model. So, here is the input data format in the LSS model. This is Vinish slope stability analysis. The problem statement that determine the factor of safety to a geosynthetic clay liner or the geomembrane line slope in unreinforced case. So, input data, you have to put that what will be the slope characteristic. That means what will be the length of the slope measure along the geosynthetic clay liner or geomembrane, that is L is equal to 35 meter, and thickness of the cover soil small h is equal to 0.3 meter, and slope angle, that is beta, is equal to 18.4. Now, cover soil have its own property. So, cover soil property is given, unit weight of cover soil, that is gamma is 17.5 kilonewton per meter cube, frictional angle of cover soil delta by pi is equal to 30 degree, and cohesion of the cover soil, that is C, is equal to the 0. Apart from this, you have to provide with the properties of the geosynthetic clay liner and the geomembrane property. So, adhesion between the geosynthetic clay liner and the geomembrane and the cover soil, and that is C of A is equal to the 0, and interface friction angle between the geosynthetic clay liner or geomembrane and the cover soil is 15 degree. So, these are the input data are required for the Binet slope stability analysis. You have to provide with the what will be the characteristics of the slope, what will be the characteristics of the cover soil, and as well as what will be the characteristics of the geomembrane or geosynthetic clay liner. And now you can calculate. So, you can obtain the output, that is weight of the active wedge WA is 178.496 kilonewton, and weight of the passive wedge, that is WP, is equal to 2.63 kilonewton, and interwedge forces acting on the active wedge from the passive wedge, that is E of A, is equal to 2.459 kilonewton, and similarly that interwedge force acting on the passive wedge from the active wedge, that is E of P, is equal to 2.459 kilonewton. So, you calculate what will be the factor of safety. Then factor of safety Fs is equal to 0.842. Now, what will be your comment? Since the factor of safety value here is less than 1. So, the forces tending to the slide the cover soil over geomembrane or the geosynthetic clay liner are more than the resisting forces. So, the design is not stable. In this case, the sliding over the geosynthetic clay liner or the geomembrane is anticipated. So, user can use the following approach to make the design stable. So, there is a 3 option. One option is A, they provide the tapered covered soil instead of the uniform thick covered soil. If yes, you want to go for the tapered soil, then you can also calculate and also you can find out the what will be the factor of safety. I will show you in my program later on. And B, by providing the geotextile or the geogrid reinforcement along the slide slope. Because if we can provide with the geogrid reinforcement, so there will be the development of the shearing resistance between the cover soil and the geogrid material, and that will improve also the stability factor. Then see, by altering the slope geometric configuration, you can alter the geometric configuration, that is effect by decreasing the slope angle or by increasing the cover soil thickness, and you can check that whether it satisfies the factor of safety or not. So this way you can solve the problem. So here some comparison of landfill slope stability model with the Helm model. Case uniform thick unreinforced cover soil, that is with the Helm model factor of safety is equal to 0.842, and the landfill slope stability model factor of safety is 0.842. So you can see that LSL model is satisfying with the Helm model, that means it satisfies that criteria, that means LSS model is okay. Now this is the design curve for the Fs value of uniform thick unreinforced covered soil. So this is the factor of safety value 1, factor of safety 1.5 and the 2, and this x axis is the slope angle beta in degree, and this y axis is the interface friction angle between the covered soil and the geosynthetic clay liner delta in degree. And this is the problem when L is equal to 35 meter, H is thickness of the cover soil is 0.3 meter, and gamma unit weight of cover soil then is 17.5 kilonewton per meter cube, pi is equal to 30 degree, and CCA is equal to 0 kilonewton per meter. So you can obtain the curve like this for the different factor of safety. So if you know what will be the slope angle and what you require the factor of safety, the 1.5, 1 or 2, then accordingly also you will be knowing what will be the friction angle, that means what friction angle you require. Or if you know that what will be the friction angle and also the slope angle, then you can calculate what should be the factor of safety. So if the factor of safety is reasonable, so then accordingly you can select that what will be the slope angle and what will be the corresponding the friction angle between the cover soil and the geosynthetic material. 3. Vanish slope stability for uniform thickness reinforced cover soil. Now in this slope the reinforcement is added. So this is the reinforcement here, this dot is the reinforcement is here. So this is the forces involved in a finite length slope analysis for a uniform thick cover soil with reinforcement. This is after Koiner and Sung 1998. So again you know that this is WA, weight of the wedge in the active zone, and this is weight of the wedge in the passive zone, and here the slope angle is beta, and here is the development of the friction between the reinforcement and the covered soil, and that is the delta. And Na you know, so this will be Na into tan delta, and this is the length of the slope, that is L, and this is the H is the thickness of the covered soil, and this is the geomembrane, and this is the reinforcement which tensile strength value is, let us say, is equal to T. And there is also that what will be the inter-edge forces is acting, that is EA and also E of P, that is inter-edge, EA is inter-edge forces acting on the active wedge from the passive wedge, and this EP is the inter-wedge on passive wedge from the active wedge. And NA you know normal force in the active wedge, and this NP normal force in the passive wedge. So, these are the forces are involved in a finite slope analysis for uniform thickness with the reinforcement. Here we add the reinforcement. Now, this factor of safety again will be equal to minus B plus minus root over B square minus 4AC by 2A, where A is equal to WA minus NA into cos beta minus T into sin beta into cos beta, B is equal to minus WA minus NA into cos beta minus T sin beta tan pi plus NA into tan delta plus CA into sin beta into cos beta plus C plus WP tan pi into sin beta, and C is equal to NA into tan delta plus CA into sin square beta into tan pi. So, if you know this all this value WA, NA or beta, that means you know all the A, B, C, so you can calculate that what will be the factor of safety. So, now I am giving one design example of Vinit slope stability for uniform thickness reinforced covered soil. Let us say covered soil slope beta is 18.4 degree, length of the slope L is equal to 35 meter, thickness of the covered soil H is 0.3 meter, unit weight of covered soil gamma is equal to 17.5 kilonewton per meter cube, cohesion of the covered soil C is equal to 0, adhesion between covered soil and the geosynthetic clay liner CA is equal to 0, internal friction angle of covered soil pi is equal to 30 degree, interface friction angle between the geosynthetic clay liner and covered soil delta is equal to 15 degree, and tensile strength of the reinforcement T ultimate is equal to 100 kilonewton per meter, and cumulative reduction factor RF is equal to 4. So, you have to determine what would be the factor of safety against the covered soil sliding. So, here is the input data format in the landfill slope stability model. So, you need what will be the slope characteristics, that means what will be the length of the slope measured along the GCL or the geomembrane, that is L is equal to 35 meter, and then the what will be the thickness of the covered soil, that is H is equal to 0.3 meter, and slope angle is equal to 18.4. Now, what will be the covered soil property, that is unit weight of the covered soil, that is gamma will be equal to 17.5 kilonewton per meter cube, and friction angle of covered soil pi is equal to 30 degree, and cohesion of the covered soil is 0. Now, what will be the geosynthetic clay liner or geomembrane property? That means adhesion between the geosynthetic clay liner and the geomembrane and the covered soil, that is C of A is equal to the 0, and interface friction between the geosynthetic clay liner, geomembrane covered soil, that is delta is equal to 15 degree. Now, because we have added the reinforcement here to make the much more stable slope, so here we given the reinforcement detail, that is ultimate tensile strength of the reinforcement geotextile or the geogrid, and that is T ultimate is equal to 100 kilonewton. Reduction factor for installation damage, that is 1.26, then reduction factor for creep, that is R of FCR is 1.29, and reduction factor for installation damage RFID is 1.25, and reduction factor for chemical and biological degradation, that is RFCBD is equal to 2.0, and the reduction factor for SIM. So, it requires something sometimes to join the geotextile material, and that RFSM is equal to 1.25. So, you have to put all this input data, that is what is slope characteristics, what will be the properties of the covered soil, what will be the interface between the soil and the geomembrane material, and also what will be the properties of the reinforcement. Then you will have the output, that means weight of the active wedge, WA is 178.496, weight of the passive wedge, WP is equal to 2.63, and the inter-wedge forces acting on the active wedge from the passive wedge is EA is 1.216 kilonewton, and inter-wedge forces acting on the passive wedge from the active wedge, that is EP is 1.216 kilonewton. So, you know that WA, WP, EA, EP, you can calculate the what will be the factor of safety. So, factor of safety is 1.507. So, comment, since the factor of safety value is greater than 1, that is the force tending to slide the covered soil over the geomembrane or geosynthetic clay liner are less than the resisting forces. So, design is stable and safe. Now, this design is for static condition only, but do you want to include the seismic analysis in this design? Yes, you can, and also you can calculate what will be the factor of safety due to the seismic design. I will show you later. Now, this is the design chart for uniform thickness reinforced covered soil. So, this is the slope angle beta in degree, defined slope angle, and the corresponding what will be the allowable tensile strength. Now, here this is the curve for the different factor of safety, value is 1.0, 1.5 and 2.0. And the problem is that length of the covered soil is 35 meter and thickness of the covered soil H is equal to 0.3 meter and unit weight of covered soil 17.5 kilonewton per meter cube, and angle of friction pi is equal to 30 degree, and CA is equal to the 0 kilonewton per meter square, and delta is equal to 15 degree. So, knowing that what should be the slope angle and the required factor of safety, so you can calculate what will be the allowable tensile strength of the geosynthetic material, or knowing the geosynthetic material and the slope angle, also you can calculate what will be the factor of safety from this design chart. And this design chart for uniform thickness reinforced covered soil. Now, here shows the comparison result from the landfill slope stability model and the help model. Case, when the reinforced case, when the ultimate tensile strength of the geogrid is 100 kilonewton per meter and cumulative reduction factor 4, then help model you are having that factor of safety is equal to 1.506. In case of landfill slope stability model, factor of safety Fs is 1.507. Also provide us the choice to include the seismic force. Here you can choose, you can go for the seismic force also. So, in case of the reinforced case, that Helm model and the LSS model is matching very well. When the reinforced case, the T ultimate 500 kilonewton per meter, that means reduction factor is equal to 4. Then, in case of the Helm model, the factor of safety giving minus 0.701. That means it is a negative value. That means it gives a negative value in practically, which is not possible. But in case of LSS model, this software suggests that we have selected a reinforcement having higher tensile strength than required. So, choose a geogrid or geotextile with lower tensile strength. So, there is an option, so you can select the proper kind of the reinforcement which the LSS model will give the response, but Helm model does not give the response. Now, 6, the seismic analysis in Venice slope stability for uniform thick cover soil without reinforcement. So, we are considering here limit equilibrium force involved in a pseudostatic analysis after Cohen et al. 2002. So, here you can see this is the slope whose angle is equal to the beta, and this is the active wedge. Here you know what is WA, weight in the active wedge, this is the passive wedge, this is W of P, and this is the geomembrane, and this is the thickness of the cover soil, and this is the length of the slope is L. Here that we have considered that seismic, that means the C of S, the CS is the seismic coefficient. So, here it is WA due to seismic coefficient, so you have to take into account that CS into WA in the active wedge. Similarly, in the passive wedge, this is the WP, weight in the passive zone, and this is the CS into WP. What CS is the seismic coefficient. So, CS into WP. So, this seismic force in the active wedge and passive wedge are to be taken into consideration for the in pseudostatic analysis. Now, again the factor of safety is equal to minus B plus minus root B square minus 4AC by 2A, where A is equal to CS into WA plus NA into sin beta into cos beta plus CS into WP into cos beta. Then B is equal to minus CS into WA plus NA into sin beta into tan phi plus NA into tan delta plus CA into cos square beta plus C plus WP tan phi into cos beta, and C is equal to NA tan delta plus CA into sin beta into cos beta into tan pi. Here that C of S is the average seismic coefficient. So, what it has been added. So, this is one design example inclusion of the seismic forces in a Venice slope stability analysis for unreinforced case. Cover soil slope beta is equal to 15 degree, length of the slope L is equal to 30 meter, and thickness of the cover soil H is equal to 0.35 meter. Unit weight of cover soil gamma is 18 kilonewton per meter cube. Cohesion of the cover soil C is equal to 0. Adhesion between cover soil and the geosynthetic clay liner or geomembrane CA is equal to the 0. Interface friction angle of cover soil pi is equal to 32 degree, and interface friction angle between geosynthetic clay liner or geomembrane and cover soil delta is equal to 18 degree. Average seismic coefficient CS is 0.1. You have to determine the factor of safety against the cover soil sliding. So, here is the seismic analysis for Venice slope stability. This problem statement, this slope stability program utilized in a pseudostatic analysis to determine the factor of safety of a geosynthetic clay liner slope, and this is a unreinforced case. So, input data, the slope characteristics, that is the length of the slope measured along the geosynthetic clay liner L is equal to 35 meter, and the slope angle beta is equal to 15 degree, and then the thickness of the cover soil, that is H is equal to 0.35 meter, and cover soil properties is the unit weight of cover soil, that is gamma is 18 kilonewton per meter cube, and cohesion of the cover soil, that is C is equal to 0, and friction angle of the cover soil, that is pi is equal to 32 degree. and then geosynthetic clay liner or geomembrane property, that is interface friction angle between the geosynthetic clay liner or geomembrane and the cover soil in degree, that is delta is equal to 18, and then the addition between the geosynthetic clay liner and the geomembrane cover soil is Ca is equal to 0. Here we are considering the seismic analysis for beneath slope stability. Therefore, the seismic characteristics also here to take into account. So, average seismic coefficient, that is Cs is equal to 0.10. So, now you can calculate and you can obtain the output data, that is weight of the active wedge WA is equal to 1.661, weight of the passive wedge WP is equal to 4.412, and that interwedge forces, that is acting on the active wedge from the passive wedge in kilonewton EA is 3.306 kilonewton, and interwedge forces acting on the passive wedge from the active wedge, that is E of P is equal to 3.306 kilonewton, and this factor of safety Fs is equal to 0.905, and factor of safety in the static condition, that is Fs will be equal to 1.273. So, what is the comment? That since the factor of safety value in the seismic condition less than that of 75% of the factor of safety value of the static condition, so design is not the safe. In this case, the sliding over geosynthetic clay liner or geomembrane is anticipated. So, user can the following approach to make the design stable: A, by providing the geotextile or geogrid reinforcement along the side slope, or B, the alternating the slope geometry configuration either by decreasing the slope angle or by increasing the cover soil thickness. So, these are the two options. So, you can go the both the option and can check whether it is stable or not. Now, this is the comparison of the landfill slope stability model with the Helm model. Case when it is unreinforced scale, Helm model factor of safety 0.905 and LSS model Fs is equal to 0.905. Since the factor of safety value is less than 1, so design is not stable. So, it gives us the two solution for the particular case to increase the factor of safety value. So, we can go ahead with these two options. You can make the slope either in the stable or the berm or the anchor, or you can provide with the geogrid or geotextile reinforcement to make it a stable when the factor of safety will be the greater than 1. So, with this I finish my lecture today. Let us hear from you any question. Thank you for listening.